Welcome, technical listeners, AI researchers, and ML engineers to AI Paper Slop.
Glad to be here.
So today we are diving right into a brand new paper. It's called ClawGym-2, Exploring Black Box RL on Agent Harness.
By the researchers at Renmin University of China and iQuest Research.
Right. And look, we're skipping all the traditional pleasantries today because the core insight here is just too important.
It really is.
This paper essentially solves the problem of doing reinforcement learning on large language models through complex, opaque agent harnesses, things like Claude Code or OpenClaw.
Which has been a massive headache for the field.
Absolutely. So they introduced this unified black box RL framework. It uses a sandbox infrastructure and a serving proxy to capture model calls. Then it reconstructs them into prefix trees and adapts PPO and GRPO for optimization.
Right.
And the result? Roughly 10 to 15 point improvements in pass at 1 on benchmarks using a Qwen 330A3B backbone, which proves you can stably train agents across heterogeneous black box execution systems.
Yeah, and we really need to emphasize why this matters to you, the listener, because modern agents, they don't just chat anymore.
No, not at all.
They rely heavily on these incredibly complex harnesses for tool orchestration, for workflow routing, for everything. But until now, optimizing a policy through these opaque systems has been basically an unstable nightmare for RL engineers.
Yeah, let's unpack this. Because to understand the solution, we have to unpack why standard RL fails when a harness gets in the middle.
Right.
Imagine you are tasked with debugging an open source library. You can see every stack trace.
Sure, it's all right there.
That is traditional white box RL. But black box RL is like trying to optimize API calls to a closed source legacy enterprise system.
Oh, that's a great analogy.
Right. You only see the requests you send in and the final output you get back. You have absolutely no idea what kind of spaghetti logic is happening inside.
Exactly. And the evolution of these systems makes it so apparent. I mean, think back a couple of years, we had simple React loops.
The good old days.
Right. You prompt a model, it generates a thought and an action, your Python script parses it, runs a basic function, feeds the observation back. It was totally observable.
But production-grade harnesses today, like Claude Code or Codex, they abstract all that away.
Yeah, completely. They handle complex tool interfaces natively. They have silent retry mechanisms. So for the model, the interaction protocol is just, well, workspace, context, and action go in.
And then eventually an updated workspace, context, and observation come out.
Exactly. The harness is a total black box. You have zero visibility into the context, compaction, or sub-agent routing inside.
Which creates a huge problem.
It creates three fundamental challenges, actually. First, scaling stateful environments for concurrent rollouts without crashing. Second, extracting coherent RL trajectories from fragmented, redundant model calls.
Because it's just a mess of data.
Right. And third, creating a system that is extensible across totally different heterogeneous harnesses. You don't want to build $1 million pipeline for Claude Code and then start from scratch for OpenClaw.
No, you definitely don't. So since we can't look inside that black box enterprise system, we have to isolate it and intercept the calls.
That's the only way.
And the execution infrastructure they built for this is wild. They encapsulate each task-specific environment, which is initialized from a workspace, and its harness inside a temporary isolated sandbox.
Which is key for those massive concurrent rollouts.
Right. And crucially, they use MCP, or Model Context Protocol servers, inside the sandbox to standardize tool access, like web search.
Yeah, MCP is becoming standard for a reason.
But to decouple the policy optimization from the harness execution, they put a serving proxy right at the model boundary.
This is the critical piece.
Yeah, this proxy intercepts every single model request, invokes the current rollout policy, and records the exact tokens and log probabilities.
It just sits there and catches everything.
It does. But I do have to ask, what about the overhead? If every rollout gets a bespoke sandbox that's destroyed right after, how on earth do they handle the inevitable infrastructure failures?
Like network timeouts and stuff.
Yeah, exactly, without poisoning the RL data. Because if a network timeout looks like a task failure to the RL algorithm, your data is ruined.
Right. Well, what's fascinating here is how they handle the fail-safes. They are incredibly rigorous. If a task hits an HTTP error, the system just drops it completely.
Just throws it out.
Yep. They also enforce hard wall clock timeouts and forcibly terminate tasks that hang. But the most crucial one is what they call complete trajectory capture via settling.
Via settling, what does that mean?
So black box harnesses are heavily asynchronous, right? Just because it finished an external request doesn't mean all the state records are written. It might be running background retries.
Oh, right. Spinning down a subagent or something.
Exactly. So the proxy actively waits. It waits for those async harness retries to finish, basically waiting for the dust to settle before it actually logs the trajectory.
Wow. Okay, so now the proxy has captured all these intercepted model calls.
Huh.
But we run into the next problem. The data is an absolute mess.
It's just a chronological time series of text generation requests.
Right. How do we turn that into usable RL trajectories? Because the calls are fragmented, they're forked, they're full of redundancies due to those harness retries.
Yeah, the harness might have silently caught a syntax error and prompted the model again without you knowing.
So they organize these calls into a prefix tree, and it's rooted at the initial task prompt. Any shared interaction histories get merged into common tree nodes.
While distinct continuations, when the model tries two different approaches, those become separate branches.
But honestly, my first thought was, why not just flatten it?
Oh, you really don't want to do that.
Well, think about a Git repository. If we flatten a complex Git tree into a single commit history, we lose all the context of the abandoned branches and merges.
Exactly.
So flattening the RL trace would mean the model trains repeatedly on the same shared history, which would just destroy the long horizon structure of the task, right?
It would massively overweight those early steps. So the tree structure is essential. But a raw tree still has too much noise, so they apply some very rigorous filtering to it.
Okay, what kind of filtering?
First, they remove dead leaves. These are basically failed generation retries that the harness itself discarded. Sibling trajectories that end there are just tossed.
Makes sense.
Then they discard overbranching tasks. If a rollout is stuck in an infinite failure loop, just spamming the same broken bash command, that whole thing is thrown out.
Good, because that's useless data.
Right. And finally, they exclude auxiliary trajectories. If the harness spins up a background subagent, those branches are cut. You only want the main task-solving trajectory to get the terminal reward signal.
Right, because you don't want to reward a background web search agent for completing a massive coding task it didn't actually do.
Exactly. It would ruin the credit assignment.
Okay, so with a clean prefix tree mapping the exact interactions, we actually have to run the RL math over this weird data structure.
Which is not trivial.
No, not at all. They test both critic-based PPO and critic-free GRPO. For GRPO, advantage is estimated relative to a group of rollouts.
Like maybe 8 rollouts per task?
Yeah. The rollout level reward is normalized against those group statistics, and the advantage is applying to all trainable token nodes in that rollout's tree branches.
GRPO handles the tree structure pretty naturally.
But here's where it gets really interesting. Applying PPO to this is incredibly complex because calculating temporal credit assignment across forked branches is a nightmare.
A computational nightmare. Backpropagating across divergent futures is just too much.
So they simplify it. They treat trajectories independently. They set gamma to 1 and lambda to 1, which means generalized advantage estimation just degenerates to the final reward minus the value estimate at the current state.
Yeah.
But wait, doesn't setting gamma and lambda to 1 force the value model to carry a massive burden? It has to predict the absolute final outcome from every intermediate state without any temporal discounting.
It is a colossal burden, yes. And theoretically, this simplification increases your advantage variance significantly.
I would imagine so.
But it avoids that computational gridlock we just talked about. And the findings on the training dynamics are super interesting. Both algorithms successfully stabilized over 200 to 400 steps.
Oh, wow. Both of them.
Yeah. But PPO, despite that heavy burden on the value model, actually showed smoother entropy dynamics. GRPO achieved comparable final results but had much larger variance during training.
That's fascinating. Okay, so the RL math works, but there is a very sneaky mismatch lurking in this setup.
Oh, you mean between the inference server and the training engine?
Yes, the token in, token out consistency problem. Because harnesses are notorious for secretly reformatting model outputs.
Oh yeah, normalizing JSON, stripping white spaces.
Exactly. Say the model outputs a JSON, the harness parses it, executes it, and then feeds a perfectly normalized JSON back into the context. If you train on that retokenized output, you're training on text the model didn't actually generate.
Which introduces massive off-policy bias.
Right, so they use this token in, token out discipline. They keep 2 decoupled views. The exact generated tokens are grafted onto the training tree, while the harness only ever sees the decoded text it's allowed to manipulate.
It's such a necessary fix.
And to fix the probability mismatch between the inference engine and the training engine's forward pass, they apply a token-level importance sampling rollout correction.
Right, scaling the loss by the ratio of the probabilities.
Yeah. And speaking of engineering details, did you catch the buffered pseudo-streaming parsing safeguard?
Yes, that was brilliant.
It's so cool. So incremental streaming parsers in harnesses often prematurely terminate valid tool calls, right? If the model hasn't finished the JSON, the parser tries to read it, fails, and crashes the connection.
Which is so frustrating.
It reminds me of a UI bug where an app registers a click before the page fully loads and everything just breaks.
Exactly like that.
So they fixed this by buffering the tokens while sending synthetic service and events to keep the connection alive. It's a brilliant, hacky fix to preserve the streaming interface while bypassing those parser errors.
It really is. And if we connect this to the bigger picture, these engineering details are what make or break RL at scale.
Absolutely.
Off-policy bias and parsing crashes are the silent killers of Agentic RL. Fixing them is arguably just as important as getting the mathematical loss functions right.
I agree completely. So with all that infrastructure bulletproofed, what happens when we actually train the models? And can we train on multiple different harnesses at once?
This is where the results get really fun.
Yeah, they tested Quinn 3.8b and Quinn 3.38.3b on ClawGym-Bench and PinchBench using OpenClaw and Claude Code, and the results are just massive.
The jumps in performance are huge.
Yeah, Claw 2 OC38.3b improved pass at 1 by 9.98 points on ClawGym and 11.71 on PinchBench.
And the Claude Code version was even better.
Right. Claw 2 CC38.3b improved by 14.81 on ClawGym and 17.28 on PinchBench.
On a fixed 30 billion parameter backbone, that's not trivial.
And then they introduced mix harness training, feeding one model rollouts from both OpenClaw and Claude Code simultaneously.
In the exact same training batch.
Yes. They just normalized advantages strictly within task harness pairs, so the math didn't bleed. And that mixed model matched or beat the single harness models.
Proving it can learn the distinct dialects of different harnesses without getting confused.
So what does this all mean? I want to zero in on the JobBench and OfficeQA results for a second.
Yeah, let's talk about those.
Because JobBench requires reading heterogeneous files like images and databases. And OfficeQA is this really dense document reasoning.
Right, it's not just basic coding tasks.
Exactly. And this framework improved JobBench Easy from 20.46 to 27.20, and OfficeQA Full went from a dismal 8.53 up to 21.54.
That's a huge relative jump for OfficeQA.
It is, which proves it isn't just overfitting to a specific coding sandbox. It's genuinely learning how to reason and operate the harness across multimodal problems.
It's learning to pilot the software. Though we should definitely add some nuance regarding the initialization here.
Oh, right, the cold start ablation.
Yeah. The paper tested cold start initialization. That's where you do a lightweight supervised fine-tuning on successful trajectories before starting the RL phase.
Versus just starting raw from the base model.
Exactly. And while both methods worked, the cold started model had a much higher starting reward. It also had a significantly smoother upward trajectory during optimization.
And it avoided that entropy collapse, right?
Yes, it totally avoided the late-stage entropy collapse we mentioned with GRPO. It proves that even with all this robust black box infrastructure, a good behavioral prior is still highly valuable.
It gives the model a solid foundation before you unleash the RL.
Precisely.
So to cap off this discussion, I kept thinking while reading this, was this entire black box infrastructure actually necessary?
It's a fair question. Why go through all the trouble?
Right. Why build all these sandboxes and proxies? What if we just built a fully transparent white box agent loop, where every state transition is totally observable from the start?
Well, the researchers actually tested exactly this.
They did. They built a white box agent loop with standard tools, bash, search, fetch, Python file tools, and the white box 30A3B model achieved an impressive 59.90 pass at 1 inside its own white box loop.
It performed phenomenally well in its native environment.
But here is the crucial generalization question. Did that white box intelligence transfer when they dropped it into the black box OpenClaw harness?
And here is the paper's final twist.
Drumroll, please.
It transferred a bit. It scored 50.33 under OpenClaw, which is a 5.22-point improvement over the raw base model. So some reasoning definitely carried over. But it still lost significantly to the Claw 2 OC30A3B model.
The one trained directly inside the black box OpenClaw harness.
Yes. That model scored 62.62. That's a nearly 12-point gap.
Wow. which definitively proves that models need to learn the specific idiosyncratic interaction patterns of their target deployment harness to maximize performance.
You cannot just train an agent in a sterile white box environment and expect it to survive contact with a complex production harness. The training environment has to mirror the deployment environment.
Even if that environment is a totally opaque black box.
Period. It validates the entire premise of the framework.
It's honestly a remarkable piece of engineering. Well, thank you to everyone for joining us on this deep dive on AI paper slop.
It's been a great discussion.
But before we go, I want to leave you, the listener, with a final thought to ponder.
Oh, I like where this is going.
If we can successfully perform reinforcement learning on models interacting with closed-off, opaque software systems, what happens when we point this framework not at agent harnesses, but at fully closed API ecosystems?
Wow.
Like, imagine letting an agent run RL against a proprietary cloud architecture or a live commercial algorithmic trading platform, where we only see the API requests going in and the financial outputs coming out.
The boundary between AI model training and real-world software execution is officially blurring. If the system is a black box, this proves we can still learn to master it.
Exactly. Something to think about until next time.